Hello, everyone. So last time we were looking at solutions of second order differential equations. Last time we saw that, let's say if you have y double prime plus p of x times y prime plus q of x times y equals 0. And if y1 and y2 are two linearly independent solutions, then any solution will be of the form C1y1 plus C2y2. So a linear combination of linearly independent solutions. This will be the general solution, and the solution for this equation will exist and will be unique. So the existence also saw that the existence and uniqueness are guaranteed if, or let's say under the assumption of continuity. So if all functions that we have are continuous, p of x and q of x are continuous, and also if the initial conditions are given. This is a second order differential equation, so we need two initial conditions. If two initial conditions are given and the functions that we have p of x and q of x are continuous, then we can say that the solution exists and is unique. The existence and uniqueness are guaranteed under the assumption of continuity. Continuity is one condition, and also if two initial conditions are given. Two initial conditions are given. So this is about existence and uniqueness of solutions and how to find a general solution if we have two linearly independent solutions. Now, we want to look at how we can find the solutions. So now the question is how to find solutions, how to find, let's say, the general solution if we have access to one solution. So one solution, let's say y1. Let's say for some reason or with some method, let's say it could be by guessing or some other method, we have access to one solution, we have found one solution, and we want to find a second solution. And we know that a second linearly independent solution, and we know that once we find two linearly independent solutions, then we can find a general solution. So how to find general solution if you have access to one solution, y1. So let's write the other solution, y2. Let's write y2 in the form y2 equals, let's say, y1 times v for some function v. I want to write y2 in this form. So no matter what y2 is or what y1 is, if you basically divide y2 by y1, so as long as y1 is not zero, zero function, then we can write y2 as y1 times v, because we can just simply write v as y2 divided by y1, and then y2 will be y1 times v. So as long as y1 is not zero function, we can always write y2, our second function, that second solution that we want to find it, we can write it as y2 equals y1 times v. So basically the goal here is to find V. So we need to find V in order to find Y2. So we know that Y2 is supposed to be the solution for our equation. So Y2, Y1 and Y2, both of them basically, Y1 and Y2 are the solutions of y double prime plus p of x times y prime plus q of x times y equals 0. So this is the original equation, and y1 and y2 are solutions of this equation. Now y2, so that means y2 satisfies the equation. If y2 is in particular a solution of this equation, means y2 satisfies the equation, meaning that y2 double prime plus p of x times y2 prime plus q of x times y2 equals 0. Now what will be y2 prime and y2 double prime? Let's see. So y2 prime is derivative of this function. We have to use the product rule. If I use the product rule, I'll get y1 prime times v plus v prime times y1. And then the second derivative, y2 double prime, will be derivative of the right-hand side. Again, I have to use product rule for each term. So y1 double prime v plus v prime y1 prime plus another v prime y1 prime plus v double prime y1. So this one I can write it as y1 double prime v plus 2v prime y1 prime plus v double prime y1. So this will be y2 double prime. Now if I replace it, substitute back, I'll get y1 double prime v plus 2v prime y1 prime plus v double prime y1. So this is a whole three terms all together are y2 double prime, and then plus p of x times y2 prime. y2 prime means y1 prime v plus v prime y1 plus q of x y2 was y1v equals 0. So then if we arrange the terms together, there are a few terms that all contain v. So for example, this one contains v only, this one contains v only, this one contains v only. Let me take v out from these three terms. So I want to regroup the terms together. So let me write this term with this term with this term together. So then I'll get rearranging the terms. We get v times y1 double prime plus p of x y1 prime plus q of x y1. I want to regroup the other terms. So look at here, v prime. Now this term contains v prime, this term contains v prime. So let's write these two together. So v prime, take v prime out, times 2y1 prime, 2y1 prime plus the other term is p of x times y1, p of x times y1. and also v double prime. V double prime, the coefficient is y1. So v double prime times y1 equals 0. Now this term is going to be 0 because y1 is the solution itself. Y1, if you remember, is the solution of this equation. So if y1 is a solution of this equation, means if you substitute y with y1 here, it will satisfy the equation, meaning that y1 double prime plus p of x y1 prime plus q of x y1 will be 0. So this will be 0. And then we have v prime times this guy, and v double prime times this guy equals 0. So then I can write it as v prime times 2y1 prime plus p of x times y1 plus v double prime times y1 equals 0. So this will be the equation that v must satisfy. And as you can see here, there is no v term. So it's just v prime and v double prime. The v term already vanished. So how can I take advantage from this situation? So let's set v prime as another variable, let's say w, because if I set v prime as w, then v double prime will be w prime. And instead of having a second order differential equation, we will have a first order differential equation, which is a very good news because, you know, if I can manage to reduce a second order differential equation to a first order differential equation, that's a great news because we already spent a full chapter about how to solve a first order differential equation, and we already know different methods how to solve it. So if we can reduce a second order differential equation to a first order, that's a great news. We can use the methods we learned before to solve that equation. So let's set w equals v prime. Then v double prime will be w prime, and the equation above will be reduced to w times 2y1 prime plus p of x times y1 plus w prime times y1 equals 0. So this is a first order ODE. Solve it for w, and then find v such that y2 equals y1 times v becomes linearly independent with y1, i.e. meaning that y2 and y1 must not be scalar multiplication of each other. Because after you find w and then you want to find v, there could be some constants involved. There could be some constants involved that you can choose the constants. You can choose those constants whatever way you want, but the only thing that you have to make sure that happens is that you choose the constants appropriately in a way that y2 and y1 will not become scalar multiplication of each other. And y2 is y1 times v, so that means that you have to make sure, so this is equivalent with saying that v, you cannot choose v as a constant. Any other choice? For V leads to a linearly independent solution y2. See, for two vectors, we know that they are linearly independent if they are not scalar multiple of each other. So this rule is valid only for two vectors. So if I have, for example, one vector v and another vector 5 times v, then they are linearly dependent. But if I have two vectors that are not scalar multiple of each other, then they are linearly independent. Now, y2 is y1 times v. You want y2 to be linearly independent from y1. So that means y2 cannot be or must not be a scalar multiple of y1, but y2 is y1 times v. So that means v cannot be a scalar. So that's why the only choice that you should not choose is v to be a constant. If v is not constant function, then y2 will not be a scalar multiple of y1, and therefore y2 and y1 will be linearly independent. So this explanation that I wrote here from here to here is because after you solve this first order differential equation, you will find W, it will include some constant. After you find W, you want to find V, again, it will include some constant. So there will be two constants involved that you want to choose. And I'm saying that choose those two constants in a way that V does not become a constant function. Because if V becomes a constant function, Y2 becomes a scalar multiple of y1, and y2 and y1 will become linearly dependent, but we want y2 and y1 to be linearly independent. So that's the only restriction that you have to think about when you're solving this equation, when you're solving for W, and then when you're solving for V. Now let's look at an example of this situation. I will explain in an example, and I hope that clarifies the situation better. So let's look at an application of this method. So we want to solve y double prime plus, let's say by prime plus cy equals 0 with a b squared minus 4c equals 0. So let's say we have an ODE of this form, y double prime plus by prime plus cy equals 0 with the condition b squared minus 4c equals 0. So you may say, well, what about if b squared minus 4c is not 0? B squared minus 4c could be positive, could be negative, could be 0. So first of all, you may say, why b squared minus 4c? So you will see that there is solving second order differential equation will be connected to solving second degree equations, quadratic equations. In quadratic equations, in order to solve them, we have to consider the discriminant. Like if you have ax squared plus bx plus c equals 0, then the discriminant delta is b squared minus 4ac. But I can always assume that a is 1 because I can always divide both sides by a. If I divide both sides by a, then this becomes 1. So after dividing both sides by a, I can assume that this leading coefficient is 1, and then I'll have x squared plus bx plus c equals 0, and discriminant of this equation is b squared minus 4c. And in order to solve this equation, it's important whether b squared minus 4c is positive or negative or 0. If it's positive, two distinct real solutions. If it's 0, one real solution, and if it's negative, no real solution, and only two complex solutions. So similar situation happened for second order differential equation. So here we don't have algebraic equation, here we have differential equation, but as we'll see also later in this course, there is a connection between solving algebraic equation and solving differential equations. So in particular here, solving second order differential equation is connected to solving second degree algebraic equation. So it's similar to algebraic equation that the value of discriminant is important, whether it's positive or negative or zero. Same thing happens here. And the value of discriminant is important, whether positive or negative or zero. So right now we want to start with the case where a discriminant is zero. We assume discriminant is zero. And after that, we'll consider the cases where discriminant is positive or negative. We'll solve all those cases and we'll find the solution in all those cases and possibilities. So let's start with assuming that the discriminant b squared minus 4c is zero, and let's see how we can find this solution. So we have an equation y double prime plus by prime plus cy equals 0 with b squared minus 4c equals 0. So first, let's try to find one solution. Because according to the recipe that we provided, if we have access to one solution, then we know how to find the second solution. Remember, second solution here. If we have access to y1, then we can solve for w, and once we have w, we can find v, and then the second solution will be y2 equals y1 times v. So according to algorithm above, if we can find one solution y1, then we can find v that gives us y2 equals y1 times v. So, and in order to find y1, so first we need to find y1. In order to find y1, let's consider y1 to be a function of the form y1 equals e to power rx for some constant r. Let's assume y1 is e to power rx. So why are we assuming that y1 is e to power rx? Well, if we didn't have a second order differential equation, let's say if we had first order differential equation, for example, by prime plus cy equals 0, or let's say y prime equals some constant times y, then we know that the solution can be written in this form. Now that we have second order, so the very first thing we can try is we can say, why don't we try a solution again of this form? Maybe it works. If not, we can try other functions. But exponential functions are a very nice function. The derivatives of those functions is constant times the original function. So the derivative is very nice. The functions are smooth. And there are also solutions for first order differential equation. So why don't we try those functions for second order differential equations as well? They're very nice functions. Maybe we can find a solution. If we couldn't find a solution, then we can try another type of function. So these are the reasons that we can start by trying a function of the form e to power rx, a simple exponential function, as our first solution. So if y1 is e to power rx for some constant r, then what will be y1 prime? Y1 prime will be r times e to power rx, and y1 double prime will be r squared e to power rx. The first derivative will be r e to power rx, second derivative r squared e to power rx. And what do we know? We know that y1 double prime plus b. We know that y1 double prime plus b y1 prime plus c y1 equals 0. So that gives me r squared e to power rx plus b r e to power rx plus c e to power rx equals 0. Now, if I take e to power rx out as a common factor, e to power rx times r squared plus br plus c equals 0. And exponentials are always positive. So I can say that r squared plus br plus c must be equal to 0. Now you can see why I said that solving second order differential equation is connected to solving second degree algebraic equations. Here I have a quadratic equation, which is not a differential equation. R here is a constant, and then I have r squared plus br plus c equals 0. I want to find r. Basically, r is my unknown, and this is simply a quadratic equation. And we know how to solve quadratic equation, which is using discriminants. And that's why discriminant appeared earlier in my statement. So what is the solution for this now? So the solution for this quadratic equation is given by r equals minus b plus or minus root b squared minus 4c divided by 2. And b squared minus 4c is 0 according to my assumption. So then I can write this one as minus b over 2. So r equals minus b over 2. And y1 will be, remember what was y1? Y1 was e to power rx, and r is minus b over 2. So y1 equals e to power minus b over 2 times x. So this is the first solution of our ODE. The first solution of y double prime plus b y prime plus cy equals 0 with b squared minus 4c equals 0. Next, we need to find y2. Y2, which means the second solution. The second solution. And how do you find a second solution? So again, according to algorithm above, we could write y2 as y1 times v. And how did you find v? Basically, we found w, which was v prime. So to find v, solve for w, which was v prime. And what was the equation for w? So let me call this equation, maybe I can call it equation 1. Equation 1 above. So what was this equation? Equation 1. W times 2y1 prime plus p of x times y1 plus w prime times y1 equals 0. And then y1 is e to power minus b over 2 times x. So w times 2 times the derivative of this guy is 2 times minus b over 2 e to power minus b over 2x. Plus p of x here is b. So plus b times e to power minus b over 2x plus w prime times y1. y1 means e to power minus b over 2 times x equals 0. So we have this equation and we want to solve for w. So let's factor e to power minus b over 2x out again as a common factor. And then we'll get e to power minus b over 2 e to power minus b over 2x times a minus bw plus bw. This is minus b times w plus b times w plus w prime equals 0. So minus bw plus bw, they cancel out each other. And then we'll get e to power minus b over 2 x times w prime equals 0. And again, exponential functions are always positive. So that means w prime must be 0. And that means w is equal to some constant, let's say d1. A constant function. And w is v prime. So that means v prime is equal to d1. And that means v of x or v of x is equal to d1x plus d2. If v prime is d1, then v is antiderivative of d1. d1 is a constant. Antiderivative of the constant d1 is d1x plus d2. And then, so this is a solution for v. And then we will have y2 equals y1 times v, which is going to be e to power minus b over 2x times d1x plus d2. So this is a solution for y2. And we have to choose d1 and d2. We can choose d1 and d2, as we said earlier, whatever way we want to do. The only condition that we have to consider is that we have to choose them appropriately in a way that y2 is linearly independent from y1, meaning that y2 is not a scalar multiple of y1. So need to choose d1 and d2 such that y2 is not a scalar multiple of y1 equals e to power minus b over 2x. See above. For example, we can choose d1 to be 1, d2 to be 0. If I choose this d1 to be 1, d2 to be 0, then y2 will be x times e to power minus b over 2x, which is not a scalar multiple of e to power minus b over 2x. But if you do the other way around, let's say if you choose d1 to be 0, d2 to be 1, then y2 will be, again, e to power minus b over 2x, which is what we had for y1, and they are linearly dependent. If y1 and y2 are equal, they are linearly dependent. Or even if you choose D1 to be 0, D2 to be 2 or 5, let's say D2 to be 5, then 5 times this is a scalar multiple of y1. 5 times y1 is a scalar multiple of y1, and that's not what we want. So please do not choose D1 to be 0 and D2 to be constant. But if you choose, let's say D1 to be a constant, non-zero constant, and D2 to be 0, or you choose, let's say D1 and D2, both of them non-zero, those cases you get linearly independent, which is what we are looking for. But of course, it's easier to choose D1 to be non-zero, D2 to be 0. That leads to simpler choice compared to if both of them are non-zero. So you can either choose D1 to be non-zero, D2 to be 0, or both of them non-zero. But among these two choices, it's easier to choose D1 to be non-zero, D2 to be 0. Then we get E2 and Y2 equals X times e to power minus B over 2X. So this is the second solution. The second solution for y double prime plus by prime plus cy equals 0 with b squared minus 4c equals 0. And note that y1 and y2 are linearly independent, since they are not scalar multiple of each other. And so y1, y2 are not scalar multiple of each other, so they are linearly independent. And we found two linearly independent solutions for our equation, and that means we can also find the general solution. So hence, the general solution of y double prime plus by prime plus cy equals 0 with b squared minus 4c equals 0 is y equals c1 e to power minus b over 2x. But let me first write it as c1 y1 plus c2 y2. Remember, we said before that if you have two linearly independent solutions for our second order differential equation, then the general solution can be written as c1 y1 plus c2 y2, a linear combination of y1 and y2. So c1 y1 plus c2 y2, and then that can be written as c1 e to power minus b over 2x plus c2 x e to power minus b over 2x. C1 e to power minus b over 2x plus C2x e to power minus b over 2x. Now let's look at an example of this case. Example, consider, let's say y double prime plus 2y prime plus y equals 0 with, let's say y of 1 equals y prime of 1 equals 2. Find the solution. So here, what are the values for B and C? So here, B is 2, C is 1. So that means b squared minus 4c is 0. And so we are in the case that we just considered. So the solutions, the linearly independent solutions are, so as seen above, the linearly independent solutions are y1 equals e to power minus 2 over 2x equals e to power minus x, and y2 equals x times e to power minus x. And the general solution will be y equals c1 y1 plus c2 y2. So that's going to be c1 e to power minus x plus c2 x e to power minus x. And to find c1 and c2, use the initial condition or conditions here. Use the initial conditions. So y of 1 is 2. So that means c1 e to power minus 1 plus c2 e to power minus 1 equals 2. And y prime of 1 is also 2. Y prime of 1 is 2. And what is y prime? Y prime is, if I differentiate this function, minus c1 e to power minus x plus c2 e to power minus x minus c2 minus c2x e to power minus x. So at 1, if I calculate at 1, I'll get minus c1 e to power minus 1 plus c2 e to power minus 1 minus c2 e to power minus 1 equals 2. So to differentiate this function, for differentiating this function, I had to simply use chain rule. Derivative of this function is derivative of minus x, which is minus 1, times c1 e to power minus x, so minus c1 e to power minus x. For derivative of the second term, I had to use the product rule. Derivative of this function x is 1, so c2 times e to power minus x. And then derivative of this function is minus e to power minus x times x minus e to power minus x times c2. And then at 1, it will give me minus c1 e to power minus 1 plus c2 e to power minus 1 minus c2 e to power minus 1 equals 2. And then I'll get 2 equations. c1 e to power minus 1 plus c2 e to power minus 1 equals 2. Minus c1 e to power minus 1. Now this c2 e to power minus 1 minus c2 e to power minus 1, they cancel out each other. And then this will be 2. So from this one, I can find c1 to be, if I multiply both sides by minus e, so minus 2e. And if I substitute back here, c2, if I multiply everything by e, see if I multiply everything by e here, I'll get c1 plus c2 equals 2e. So c2 is 2e minus c1. So if I substitute this back here, then c2 will be 2e minus 2e, and that's 4e. So we found c1 to be minus 2e, c2 to be 4e, and then y2, and y will be equal to y was c1 e to power c1 e to power minus x plus c2 x e to power minus x. And then that will be minus 2e e to power minus x plus 4e x e to power minus x. So this is the solution of IVP above. So we found the solution of the second order differential equation with constant coefficients, y double prime plus by prime plus cy equals 0, in the case where discriminant value b squared minus 4c is 0. We still need to find the solution if discriminant is positive or discriminant is negative. We have to see how we can find the solution in those cases.